Where are we? And can you also say something once you're unmuted? Yeah,
I don't have screen sharing privileges.
let me fix that. Okay, you should be good to share.
Yep, got it. All right. Give me a second here. Are you seeing my screen?
I am.
Okay. And are you seeing, hold on one second. Come on. Are you seeing my slides advance and stuff?
Yes, Tim. It's looking good.
All right.
Okay, so we're just about ready to get started then. Okay, you good to go? Okay. All right. So welcome to day 4, folks. So we're super happy to have Niharika Sravan, who's faculty at Drexel. Over the last handful of years, she's been really leading an effort to understand how to improve the way that we do transient follow-up using data science. In particular, she's spearheading some reinforcement learning techniques that she'll talk about in reinforcement learning and some of the stuff she's been doing to try to make that happen. As you know, has probably been clear over the last handful of days, there's a lot of sort of scanning and just sort of arbitrary decision making that goes on, and Ari is trying to, improve, let's say, the methods that we use to do that. And so we're super excited to have her here to tell us all about it.
Thank you. That was such an excellent introduction. So I think, let me preface that by saying, underscoring what Michael said about decision making. And a lot of what I think about is actually how we can use machine learning to take it one step further, which is to ask, if I get a particular inference, or like, say, for example, you're getting a bunch of classifications, what does that mean for what is the next thing you need to do, given you have a particular science goal in mind? So it's that, in the realm of traditional supervised learning, you can think of them as recommender systems. But if you want something more advanced, you might want to think about more advanced approaches like reinforcement learning. You sort of like advertise this, is that this is a field that is really exciting these days, because there have been algorithms that have come out that you must be familiar with, that have had a lot of success. I, of course, mean ChatGPT, which is a combination supervised learning, reinforcement learning method. And the whole idea is that basically you can iterate, you can talk, you can improve, and the agent on the other side, which is ChatGPT, can respond to that and learn from previous interactions how to essentially respond to your request and improve its response to you. So this sequential decision making problem over a long horizon is what is reinforcement learning, essentially. That makes it significantly different from supervised learning. But in any case, I just wanted to sort of talk about why such a goal might be interesting and why you might want to do this. What is the motivation of getting this done, and what probably would be the benefits of having such a system be implemented. So essential decision making is a key. Real-time decision making is a key term here. So give me one second. I was supposed to be advancing. So as we all know, multi-messenger astronomy is a science where we put together two pieces of information. This is, of course, an illustration of 80 2017 GFO and GW 170817, which are two different transients which are associated with the same signal, that put together gave rise to your multi-messenger way of doing things. So multi-messenger, of course, to remind everybody, is not just two legs. There are two other aspects that I recently have also gotten interested in thinking about neutrinos. Cosmic rays is another sort of like a pillar in this uh, uh, arena. So you usually have a very energetic phenomenon associated with multi-messenger sources. This could range from supernovae to kilonovae, which I have alluded to earlier. These are the transients that are produced as a result of the merger of sources that are also gravitational wave sources, and AGN, which are actually more commonly associated with the neutrino electromagnetic synergy in the multi-messenger sphere. And you have tidal disruption events, which are similar in that sense, in that they are neutrinos, more expected to be neutrino sources um, than some of the others. So uh, going back to this multi-messenger picture, we want to make sure that hold on one second. I'm gonna stop sharing for 1 second. I think I'm sorry. Give me 1 second. Yep, I'm sorry. I was showing some older slides. Yep, this is what I want to do. I will pick up at the same point, but I will make sure that we're looking at the correct thing. Share screen again. Okay. Sorry. So yeah, going back, we had all these sources. So when we think about doing multi-messenger science, let's examine a little bit where the limitations might be and what we can do better. So let's let's walk through a toy scenario of how such decision making, how transient follow-up programs are being organized right now. So let's imagine that there is a gravitational wave merger that happens, and as a result of that, you have two different signals that are coming out in two different messengers. Here is Swift, that is sensitive to electromagnetic waves. Here is the gravitational wave detectors that will be sensitive to gravitational waves that will pick up the same signal. We have excellent systems in place that will do rapid inferencing and will return in a very short time scale of the order of minutes to hours public alerts that something interesting was detected, along with some preliminary information. For example, when the event occurred, where broadly in the sky was the signal, can the signal be retraced to, what is probably the distance of the source from you, and any properties associated with the compact binary coalescence. And at this point, your surveys have been obviously regularly looking at the sky. And what they may want to do at this point is make sure that the region that you're pointing to is additionally well sampled. And once this is done within, due to excellent systems that we have, processing can happen very fast. End up with a whole bunch of transients that can go through some immediate vetting. So for example, when we're thinking about gravitational wave sources, we expect the transients to be new. So the few things you may want to cut on, for example, is that there are no previous observations. So this is a new transient. It's not a known source. You go through some real bogus classification to make sure that the sources are real. And you may want to may want to impose cuts on, for example, how fast the event is progressing. And as a result of these initial sort of cuts, you may end up, initial filters, you may end up again very rapidly with several candidates that could be potential matches and could be the actual transient associated. So I've written here about less than 500. It could be any number. It could be, several tens. It could be way many more that could be matching the gravitational wave localization region. And then at this point, a lot of people who spend, a very large amount of effort will come together, and they will consider all these transients and think about how to isolate the true event from the list. And this is a huge challenge because, especially during early phases, it's very hard to tell which transient is of which type, which one is a real, maybe it's a source that is interesting for other types of science, but not for kilonovae. And the idea is that you want to be able to use very limited resources that you have on hand, that you have gotten access through blood, sweat, and tears. And you want to make sure it's allocated well so that you can get more data to make these decisions. At this point, you, for example, could be considering the host galaxy associated with these transients. You may be able to get better light curves. Maybe the gravitational wave detectors have returned better estimates of the sky maps. So you can use all of these information, but really at the end of the process, if you're lucky, you may end up with something like this. And this is actually not a kilonova. This is a very fast transient. That was a success case. But the thing to note here is essentially all the points that you're seeing in bright colors, basically. So this is a light curve as a function of time. So, this is a transient that's fading. And the thing to note is that within a few days, you literally too faint to be seeing anything. So all you get is this bunch of stuff. And this is a good scenario. This is obviously something that's hard. And I really want to, look at this entire picture and think about when we're trying to do science, we want to do this. We want to think about where we can do better. And of course, my interest has been somewhat on this side about how we can improve decision making on getting data to improve inference. So let's focus a little bit more on that aspect. So I'm going back a little bit in my story where essentially you have done some initial cuts and you have received several tens of candidates that you're looking at. And these are just a bunch of, graduate students or postdoctoral researchers who are sitting together and discussing over chat platforms or video platforms to think about situations like as follows. So here I'm giving you two examples of transients that are one of several that could be presented to you, where essentially you see a new source and in the reference image you see nothing. And as a result, a light curve is beginning to happen. And the 4 points you're seeing here are the points that would be as a result of the subtraction and the photometry that you're getting. And in this case, you can see that this is not a lot of information to go by. And as I mentioned, the goal really here is that, and there are several of these, there are just a couple. So the goal here is to essentially make sure that you're using some limited information to have, some limited resources that you have to get more information so that you can identify the real event. Where the real event may not even be visible because it's too faint, or it may look like, it may be something that is very, not obvious to you. And the second thing I want to mention, which is actually eventually as scientists, we do want to keep in mind is that when we are allocating resources to collect data, eventually that data will return and inform some physics questions to you. So another thing that you may want to do in addition to just finding the transient is to make sure that the data that you do collect is informative for a science goal that you may have. And this is something that is not possible at all for you as a human being to do in your mind, because this would require you to compute Bayesian inference via sampling for a whole bunch of extra data points along a real-time light curve, such that you optimize a global objective. It's a thing that we are not doing, and we as humans cannot do, but we should. So another thing I want to mention is that additional follow-up is critical, in that we've only seen one reliable kilonova so far. And people who have gone back and tried to do searches for transients coincident with gravitational wave signals, except they don't do it in real time, they do it archivally, have not been able to find additional sources with all the additional data processing they may have. So there is strong indication that you need to actually get more data to ensure your deciphering or decision making is good. And another thing is that say, for example, you impose some classifiers that can rank your transient list according to what may be most confident classifications, which is things that have been done so far. They don't really answer what to do in response to these classifications, and this is the decision making part, and how that may affect what you might do next. I'll talk about this a little more as to why this is limited and how we may overcome this with reinforcement learning. But these are the limitations essentially. So the thing to note is that when we want, whatever process we want to put in place to allow us to find these transients and do inference for them, we would like them to be free from fatigue and bias. Humans will make different decisions in terms of what needs to be done, and there's a reproducibility issue there. You can't do this at low latency, and you want to be able to do this in a scalable fashion. And this aspect is important because our detectors are getting more sensitive, which means a couple of things. Number one, on the gravitational wave side, you will receive several times more individual notifications of gravitation wave signals that were picked up than before. So O4 is the current observing run from the detectors, and it's already pushing out way many more alerts than it was last time, which means that the whole process with that little flow chart I was showing before needs to be repeated anywhere between like 2 times to about 10 times more. And these numbers are kind of not exact. It will really depend on how the detectors actually end up performing. But it's going to be overwhelming in that you have to do this several more times. And at the same time, you will have many very sensitive detectors that will be able to detect many more transients. So the light curves themselves, which was 500, would end up being many, many more, because you're actually looking way deeper, but with worse sampling, if you will, because even though Rubin Observatory is quite sensitive and will be issuing public alerts, it doesn't have the amount of temporal resolution to give you information. So you will end up with many situations where you have very few data points. And at the same time, these little other very precious follow-up resources that we have, we do not expect them to scale at nearly the same rate. So you're essentially having a much larger deluge with a similar number of resources where you have to still do your science. So the statement that I would like to make is that the current protocol is not sustainable or suitable to get at statistics on these events. So if you want to get large amounts where you can take a large sample of kilonovae and do a science with them, that is going to be challenging. So this is where I think I will spend a lot of time thinking about, like, how do you want to address this problem? And this is a resource allocation problem. And in the background, you see Catan, if any of you have played that game. It's also a resource allocation problem. You're, of course, playing against intelligent agents throughout the board. In this case, we don't play against other intelligent agents, dual intelligent agents. This is also a thing. Oh my gosh, where did did my screen stop sharing automatically? Oh, do you see this still?
Yep.
Okay, I don't know why it popped, it left. Okay, I don't know, it minimized on me for some reason. Maybe I clicked something. And the reason I say this is because it's interesting. Number one, it makes the problem interesting to solve. And the other reason is that you will often hear reinforcement learning problems applied to games. So as I go forward, I will talk about it like a game to make it interesting and to see, how you could actually solve a game using machines, basically. So this is the game. This is a version of Catan, except you're playing with the universe. And essentially you have the state of the world, which is what you observe on the board. And this could be a whole bunch of information. So on the gravitational wave side, this could include some sky maps. It can include some probabilities of what the compact binary coalescence was, some statistics, etc. And then you end up with a whole bunch of light curves as follows, and they can be in various stages of evolution. You're very early in this event, and you're watching this right now. And you have several of these, less than about 500. So essentially, your goal is to make sure that you optimally allocate all your resources over all the events over 7 days. And this is your resource card, which you have access to. Some of them, this is pretty static. You won't get more resources. So this could be different, right? So you could have, for example, you could have a budget that is given to you in bulk, which is, for example, you have been awarded telescope time at LCO with some number of hours you can do observing with, which is a fixed number, and you have to allocate it over your entire search life. You could have a situation where you're very resourceful, and you have dedicated access to one telescope system, so you can make sure that you can get one data point per night in G or R, like that you can always use that. You can get access to very expensive resource. So you can get, for example, a low resolution spectrum, but you can only be sensitive to a certain magnitude, and you can get no more than 5 a night. So there can be all sorts of restrictions that you can have in terms of how you can apply your resources. So this is your resource card. So if you think about this problem, I'm sorry. Yeah. And if you think about this problem a little more, what you really want to do is first spell out a few things. So what is optimality? Like in terms of what you decide is an optimal allocation. And the second thing you want to know is how can you make such decisions without complete information, without full information, because the event is still happening. So say, for example, you decide that your goal is to identify, right? Your objective is to identify the real transient. A naive strategy might be as follows. You may say that I am going to rank all my kilonovae according to my confidence that that is the true source. So this is a probabilistic classifier. And say, for example, this is your rank list. There is several. There's a classifier that's producing the probability that something is a kilonova is 0.73, 0.12, 0.11, and so forth as a list. So the question is, if your objective is to identify the real kilonova, what do you do now? This is the decision-making part. Do you allocate your entire budget to the most confident event? Do you just put everything, all your chips onto the one that you feel is most confident? Do you allocate in some sort of like bucket filling fashion? So you keep adding, making sure that at least one of each type is allocated in order of confidence until you can go no more. Is that one thing you want to do? Do you want to make sure that you want to get data such that you improve your classification score? Or perhaps you want to improve for example, your light constraints on your light curves. So for example, you can focus on getting the decline rate nailed down a little better. So or perhaps something else that you may want to do. And the idea I want to illustrate is that this portion of like making sure that you are actually thinking very carefully about how to allocate resources is hard because the follow-up that you may do, it may be misallocated, in that you may think that this is the best allocation and you get some data on it, but whether or not you actually did well is not obvious right away. Maybe you get some data, there's a little bit of a processing delay, and you get information later on, or maybe from some other source, that this was actually ruled out. So you have all this other stochasticity that is getting imposed on your environment, and this could make your decisions not good. So maybe perhaps it was better to actually spend your resources to actually look at the lower ones and rule out the ones that are not confident. So the ideal strategy, what is the second question that I had asked, which is what is the best thing to do? The ideal strategy would be optimal given any future behaviors from your side or the side of other stochastic processes occurring in your situation. In this case, for example, the surveys are picking up more data and any information that could be revealed to you in the future. And this sounds like a hard problem, and it is, were it not for solutions that exist to solve it. So essentially what we're really thinking about is making optimal sequential decision making under uncertainty. And really the only algorithmic framework that can help you do this is reinforcement learning. which essentially allows artificial agents to learn through experience. When I say experience, it means it goes through scenarios and it tries a bunch of things and gets feedback and it tries to understand how to improve given a certain situation and how taking an action now may affect benefits achieved downstream. So the caveat here is that an intelligent agent, like the one I'm talking about, a reinforcement learning agent, can consider the full distribution of outcomes at every time step and all future all future actions and their returns, and so on and so forth, and chooses the best action right now that maximizes an overall reward throughout the whole scenario. Um, just a quick sort of spiel on this topic. Decision making under uncertainty is really not new. Thinking about design of experiments, optimal design of experiments is a field that has been around for a while, as has been the case for a lot of supervised learning approaches. This is attributed to a mathematician in the early 1900s. And in contemporary machine learning, you will hear two different words for this. It's reinforcement learning or optimal sensing. And this is a pretty old plot at this point, where Andrew Ng, who is one of the big names in machine learning, talked about how various subcategories of applying machine learning could have commercial success in the industry. And supervised learning is projected to be the fastest. The x-axis is arbitrary here, but reinforcement learning was expected to be a slow growth, but the most long-term driver of where the returns in AI would be the best. And I think it actually has done much better than this plot has you believe. I want to go back and sort of now make these things a little more robust and think about how you may want to apply reinforcement learning to solve decision making problems. And reinforcement learning is a pretty involved topic. So here I'll just give you some introductions and a way this was actually applied to solving like an identification type problem for Kilinovi using the transient light curves. But the whole reinforcement learning regime is pretty involved and takes time. So don't expect to walk away learning too much, and but if you spend the time to do it, it'll be useful. So just a few introductory things here is to just introduce the problem. Let's take this cartoon example where we're talking about a similar situation where you have sort of say, for example, the same situation where you have a whole bunch of transients that are happening, and you have your intelligent agent, which you're assigning the goal that you really have in mind, which is that I will give you a bunch of resources, make sure you acquire more information such that you can identify the event and make sure the constraints are maximizing light curve physics. So how might an agent go about solving it? A reinforcement learning agent might go about solving this. So first thing it wants to do, and in most, I think, yeah, this is actually true. In all reinforcement learning problems, you want to define it in a sequence of steps. So first thing you want to do is define something called a state space. A state space is really just the state of the world that the agent observes, and it just needs to be articulated properly. This could be features in terms of like how you have been thinking about for supervised learning in other portions. So for example, you can just take a representation of the observed light curve. So this could be just that time series. Perhaps you want to also give some vectorized representation of the image stamps and other things. So it's a mathematical representation of the world. The next thing you want to do is explicitly specify something called an action space. An action space needs to be written down really comprehensively. And in this case, for example, this is a ZTF type light curve, and I am asking the agent to think about follow-up with ZTF. So the idea is this agent can do the following things, right? It can take data in G, in R, in GR, or it can do nothing. So even though you have two different actions, the action space is a size 4. So you want to spell this out. In general, though, actions can be continuous in that you can obviously think about the previous scenario where I gave you a total observing budget, and you want to make sure that you allocate it in some bins. So say, for example, you can get some N hours overall, and you want to assign M today or M1, MT at time T, such that you're subject to a maximum of N. So that is also possible. Actions can be stochastic, which means this is not actually going to be necessarily applicable in our case. So for example, you may ask to take a data point, but for whatever reason there's a failure in the instrument. So that can be a situation where you expect to take an action, but you actually don't end up doing it. And I talked about having a variable cost and budget constraints that are also there. The third thing you want to do is sort of estimate next states or outcome states, essentially. So in this very simplified problem, imagine as if, like, you take some data and you're considering taking action, taking data in the R filter. The outcome states are basically telling you what are the distributions of answers you may get in the red filter later on. This is generally dictated by something called a dynamics or transition model, which is the underlying physics or the observing model, or what your telescope is behaving like. And in general, it can be a known or stochastic, which means you do not need, for a reinforcement learning problem, to have your transition model be specified. You can observe enough situations where you can marginalize over the you can marginalize over the dynamics and still end up with a good planning. So it's powerful in the sense that I don't need to spell out a kilonova model as long as it sees many kilonovae and can plan. So in general, you don't need to, but you can if you want, and it'll make things faster. But okay, so the first thing is the key step, really, and it's the thing that I think is probably easiest if you write it on paper, but the most if you really want to think about it. It's really about what's your reward or what's your return. So this is estimating how good are the outcome states for your objectives. So for example, how much is taking the data point in this probability space going to improve your classification accuracy, improve your physics model? This is the return part, where essentially you're thinking about how well you're doing. And this could be in supervised learning thought about as your response vector, but in this case you're stitching it together in a process where you're going from one to another as a result of some actions, and you can fan out in that tree fashion, so it's not directly correlated anymore. And in general, this can also be stochastic. In our case, this is likely not going to be the case. The returns can be stochastic. So next thing you want to do is specify a policy, which means all of this right now. What do you do about that? So this is what you really want to learn. This is in your model here is you learn a behavior policy. And the behavior policy in this case can be very simple. You take a greedy action, which means you just take whatever is maximizing your reward at this current moment, and you don't care if if you will get more data point. Maybe right now it's not best to do this, maybe you try something else. It doesn't care. You do the best always what is agreed upon right now. And in reinforcement learning, you'll also often hear about something called a Q function. A Q function is, I call it quality. I'm not sure what the origin of the word is, but Q function really tells you what is the quality of a certain state action pair, which means that if I see a certain state of the world and I take an action and I evaluate it for all actions in this, if the action space is discrete, the greedy policy will just take the action with the maximum Q. This is a very simplified formulation. Of course, it's way more significantly more complex. The entire idea in reinforcement learning, which makes it different from from supervised learning and also unsupervised learning, is this Q function is unknown, and you have to learn something unknown. So you want to take, in this example, even if you want to have a greedy policy, your Q function is something that is unknown to you, and you want to maximize over something that's unknown. So approximating this Q function is one of the big things in reinforcement learning. And finally, step 6, you do this iteratively. So the process repeats. You get some new data points. Your state space has now updated. So you now are exposing your agent to the revised state world. And then you keep iterating through until the episode ends, or you have exhausted your budget. Or you basically, in sort of like a load balancing or a cart problem, you can repeat forever. You don't have to end. Okay, so what we did is in this recent paper, we tried to apply a reinforcement learning method to try to solve the kilonova follow-up problem. We call this agent Pythia. So I'm going to go back to try to explain the problem that we try to solve. I'm going to go back to that example of playing a game. Here's your state of the world. There are going to be 9 light curves, of which one is the true kilonova. Okay, and this is like when the game begins, right? This is the game. You see just some things. This is your resource card. Your resource card is saying that you can get 1 additional data point in 3 filters. So my focus is ZTF, so I often think of ZTF. So there are 3 filters, and you can get 1 additional data point, and this will be a deep imaging. So this will be 300 second of deep imaging that you can get in 1 filter. So you're in that scenario where you were really good and you got access to 1 telescope and you guaranteed access to it, nearly guaranteed access to it. So the question here is, so you have 9 transients. One of them is the true kilonova always. There's a whole bunch of contaminants you don't really care about. You want to allocate follow-up in one filter every day for 7 days. So this event is going to last up to 7 days. It may finish earlier if it becomes too faint too fast, but you want to make sure that you allocate your budget okay, yeah. And so basically this is what you specify, right? What is your optimality condition, like what you say is optimal, and your physics objective. So the way I specified my physics objective was a reward, was a classification like objective, which said if you will get a reward 1 if you successfully allocated it to the true kilonova, and a 0 if you did otherwise. So this is only during training, which means as the agent is learning, it will get a reward 1 if it allocated it to the true kilonova without knowing where the kilonova is. And it keeps doing this until the final day, where it gets to where the episode will end. So if you're doing well, if you have learned a good behavior policy, you will do well on all time steps. So the maximum reward you can get is 7. I actually have made this 6 in my paper, because on the day 1, you basically just observe. So when you take an action, you get the data next night, if you will. So the day's observing comes, and then you get data the next morning. So you have, so an optimal agent, a very like a prophetic agent, will be able to get a reward of 6 every time. A random agent will be able to get a score of 6 over 9. So essentially, we used a reinforcement learning algorithm. This is a very simplified algorithm, and unfortunately, I don't have time. But if you and I were to sit together, I could actually walk you through how this algorithm works. But essentially, just give you a few key aspects that what we're doing really is letting the agent experience a whole bunch of scenarios where it's exposed to the game. And you keep giving it rewards, and it has to learn the optimal Q function. It's learning in a simulated environment, which means that you will learn the optimal behavior policy, and then you will take the learned Q function set and apply it to a realistic scenario. What we use is something called a linear value function approximation. So essentially, we are taking my state action feature representation, and I'm just parameterizing it by a bunch of weights W. And the idea is to learn this W. Remember, I said that you have to learn Q, but by doing this approximation, you can learn weights W. This may remind you somewhat of linear regression, and it is, except it's in reinforcement learning. So the update rules are different for how to update W as you experience many episodes. And I made some simple choices about how to represent the state of the world to the agent, which is essentially an autoencoder. And this is actually kind of fun, because you may every now and then, even though you don't need to, might end up using supervised learning or unsupervised learning, as in this case, to help the agent learn. And you use this often, for example, even in self-driving cars, even though they use reinforcement learning, their object detection algorithms are all supervised learning or unsupervised learning. So this is not what I'm going to skip, but it's quite straightforward. And if I had time, and if somebody were to sit and actually stare at this long enough and look at the little things, you can really figure this out. It's a very simple algorithm that does it. It has a certain update rule, and this is it. That's it, and everything else is just what the agent is acting. So set blah blah, that's the reinforcement learning part. That's it. And you update, you keep updating your weights, and you repeat until you converge. So we did that, and essentially what happened is as follows. So you remember I said that if you do things randomly, you can be 6/9, and this is your random score. And I train my agent, which is the blue line here, and this is the improvement in the score as a function of the number of episodes it's experienced, and it kept increasing until at some point it plateaued. And here is where you have actually the the variance. So obviously it's quite stochastic. It sometimes does very well and sometimes doesn't. So this is the variance of the score performance. And when we asked human experts, who are basically people who do this as research, asked to solve similar problems, they ended up falling here. So essentially, the agent did better than random, but it was superseded by human experts, which I guess is not surprising, because we used a very, very simple model, because this was the simplest thing we could do. But it showed promise that you can actually learn something better than doing something random. So that's what this is saying, that we don't have a very complex representation of the true Q function, which is your behavior policy. And if you can switch this to neural networks, there's a strong promise you can actually end up in this regime where you can compete with human experts. So the reason we use this very simple algorithm is that there's a theoretical convergence guarantee, which means if there is a Q function that is optimal, given your state action, given your value function approximation, if this is your true representation of the optimal Q function, you are guaranteed with this update to arrive at the optimal value. So we've actually converged the best you can do under a linear value function approximation hypothesis. So that was the best. So essentially, we don't have numerical instability issues. If you can get an answer, you will get an answer. So definitely demonstrates that the problem is learnable. We can now think about actually doing better with more complex representations. So essentially, the current work is to switch to deep Q networks, which will basically use a neural network instead of linear Q function. And there's some other benefits, especially with relation to how we're using unsupervised learning as a separate step from the reinforcement learning. It'll actually couple it in a single update, you can also do better if you have a very large state space. There's reasons for that, and I can talk about it. So if you have a very large resource card, it's better to evaluate it using a deep Q network for reasons I can, if people are interested, I can talk about. So essentially, here's a summary of like the same point that I was making. Here's a bunch of agents that participated. So Pythia is the artificial agent, and there's a bunch of human astronomers who participated, and essentially this is the best performing human agent who got a score of 3.43 on average, and Pythia got about 1.84. And there's some other numbers we tracked about their performance, which means that what are the fraction of kilonovae that was assigned at least one follow-up. So the goal was to maximize the number of follow-up, but you can think about even in cases where you did bad, did you at least assign some follow-up? And so for some reason that I don't understand, the agent did really well on this, even though it was not a follow-up objective. So it's just a side note as to like a thing that we observed. So another thing we observed, for example, is the importance of really drilling home this point that please specify your reward function well. And what happened is as follows. So what you're seeing here is a bunch of example test scenarios that was played by the AI and played by the human expert. So these are different scenarios. So for example, here you're seeing a single episode that was played. The little crosses, it may be too faint to see, but the little crosses here are the additional allocations that was made. The AI is to the left and the human expert is to the right. And the interesting thing was what happened when the AI and the human expert did not do well. So the true kilonova is marked as in here. So you can imagine a situation. Let's pick this one, for example. Okay, so this is the human expert looking at this situation in which this is the true kilonova. And the human expert is not able to identify it. This is actually a very anomalous type of kilonova. It's bluish, so they did not suspect it. But when that happened, when they were like, okay, I don't know what I'm doing, they were actually spreading their budget everywhere. When a similar situation like that happens with my AI, it really just is like, I don't know what this is. I'm just going to go after whatever I think is the best thing. So this was a very key difference that we saw. And the reason is that basically we don't update the reward function. If you don't do well, there is not meaningful updates to the weight function that tell you how well you're doing. So essentially, if it's doing badly, it doesn't care to sample. It just says, whatever, I failed. So ideally, once we looked at this, we were like, this is not good behavior. So we probably don't want that. So maybe there's meaningful, you can give reward formulations that actually encode this behavior better, but you really will get what you specify, right? So this is Goodhart's law. When a measure becomes a target, it ceases to be a good measure. So, just making sure that we specify rewards well. Another thing is that, when we did this comparison that, humans are not perfect too, when they are looking at situations like this, they have a certain pattern in mind. And when that doesn't happen, they can be caught off guard. Reinforcement learning is very, very computationally expensive. It's much more so, unfortunately, than supervised learning. So we ended up spending a lot of resources. And with climate change in full gear, I'm in Philadelphia right now, and we're going to be experiencing like 36 degrees. I don't know what that is in Fahrenheit, but very, very warm. So we should be careful and talk about climate change. So the disclosure here is that we spent a lot of carbon trying to get the agent to learn good behavior. So this was about 1,210 kilograms of carbon equivalent, which is approximately equal to a round trip flight from LAX to JFK. So yeah, any new formulations that can make this go down would be good in general. So that being said, we're very excited about like the prospects of such a method. So you eventually want to convert this to think about physics. One of the things that I am very excited about is thinking about the neutron star equation of state. And then eventually be making sure that you can have these solutions participate to get at a large diversity of kilinovae, and also prepare for Rubin. And so that, you can actually, oh my God, I don't know why it keeps skipping. So that you can actually participate meaningfully for these deeper but higher, I don't know what I said, deeper and high signal noise, but very, very faint events. So yeah, I think I have 10 minutes left, but I will pause here if people have questions. Sarah is anybody moderating? Should I don't see you, Michael.
Well, we'll moderate. So first, let's clap for Ari. Yeah. Okay. Okay. Okay, so we definitely do have a couple questions on Zoom. So let's start there. Sarah, you want to start?
Yeah. First of all, this was just a really, really cool talk. Thank you for sharing this with us. My question was about, can the agent potentially think about the fact that this game of Catan is a multiplayer game? Like, can it consider that other players have different resources and kind of take actions that complement the actions of others? Or is it like a very selfish kind of agent only?
So multi-agent systems are a thing. They are if reinforcement learning is hard, multi-agent systems are like out there. So there is something, so you can do it. There's a formalism within petting zoo. So reinforcement learning, you will need to use gymnasium for it to specify the experience. Petting zoo, I don't know why they call it that. It's a multi-agent situation where two intelligent agents are interacting. There are some adversarial formulations, actor-critic models in reinforcement learning. They're not actually adversarial necessarily, but you can have situations where you can formulate your reinforcement learning problem as a discriminator and an actor and a critic. A critic is the one that that tells apart whether you're actually tells how well you're doing, and the actor is the one that mimics your behavior policy. It's inspired by sort of agents that have conflicting goals in mind, but it's not like you adapt to an evolving something. And of course, eventually, if you really want to think about it formally, with two intelligent agents trying to maximize their own selfish objectives, you're thinking about game theory, and game theory is very, very hard. This is out there. So no, they all go into like weird territories there. This is quite simple as far as machine learning goes.
Cool, thank you.
Yeah.
All right, Meet.
Yeah, thank you so much for the very interesting talk. I really enjoyed like all of it, but I had actually a couple of questions. First, have we tried using constraint optimized linear integer programming to, schedule these things properly? Maybe that could be a very interesting way to, work through how you allocate resources to all of these different situations that we have. I I have I did some projects in that, and I realized that after that, if we use supervised learning models to this linear integer constraint problems, it becomes really easy to get solutions to that. Obviously, it gets complex as you increase in size and the complexity of your thing. But I think that would be a very nice way to get a look around through this, not just the DQ factor or the uh, reinforcement learning paths that we are going through.
Yep. Michael already shared one place where such an application is actually being thought of, which is to think about how to sort of like this is a different problem, but essentially if you have a sky map, how do you actually allocate the little tiles along the sky map so you have a maximum chance of coverage or some other optimization. So first of all, resource allocation problems can be solved in a variety of ways. You can do it in active learning. You can do it with supervised learning, which is imitation learning. You can also do it with linear programming. The thing to keep in mind is two things, which I will mention to you. For linear programming, you need to have the underlying sort of the dynamics of the transition model, so you can solve over it. If you have stochasticity, so there's a couple of ways stochasticity can enter in the light curves. You can remove them to some extent if you sort of think about let's just talk about. So one of the key issues is stochasticity, which means that the survey itself collects data according to a schedule that is not, even though it's like specified according to some broad rules, due to reasons of weather and scheduling and other things, it may not end up exactly where you want it to. So you can end up in a situation where you can actually have approximate I'm thinking of how you would formulate it in linear programming, but maybe that's too much to think about right now. But essentially you don't have a fixed way in which your problem will evolve. So you can have a light curve that can vary, light curves that can actually be sampled according to various sampling behavior that can be not exactly deterministic. The second thing we want to keep in mind is that a notion of delayed rewards, which is that even if, say, for example, you take an action right now, for example, if you want to get physics constraints out of it, you will not get that information up until at the end. So for a delayed reward formulation, it can become complicated to then include stochastic situations to ensure you still maximize, you still do well on your behavior policy. So there are probably formulations you can come up with that can remove some of the complexity. Honestly, it's not like there's not a version of this that can be written. You can write a version of this in imitation learning. The question is, will it do well, and how well will it do? And so I guess it really needs to be demonstrated. I think given how flexible reinforcement learning is, in that it doesn't need a specification of a dynamics model. It doesn't need it's okay with stochastic actions. It's okay with stochastic as long as it experiences it, and it's okay with delayed rewards. It's sufficiently generalizable that I think I want to use it. But that is not to say there are not other intelligent formulations in other ways. Like I said, imitation learning could be one, behavior cloning could be one, linear programming, active learning, all of that. Yeah, really whatever does well at the end, right?
Yeah, because as I see it, you could use them, these constraint functions and maximization functions as the rewards that you have specified in your reinforcement learning model as the objective functions for the linear integer programming that you are getting. I
Mhm.
understand that the end physics is an issue because you get the state of equational states that you want at the end.
Mhm. Right.
But resource allocation wise, I think that would be a better way to go through that. At least that's what my, and I think we can I can think more about it and get back to you on this.
Yeah, for sure. Like I said, I wanted a general. So for me, when I make an environment, which I will, it needs to serve multi purposes, right? So I don't want, like for example, I will create an environment and have my students train an agent, this agent type A for optima, goal blah. As long as it's sufficiently, it's really like, for me, it's a very flexible framework for, and it checks off so many of the objectives I like, that I find it, and I don't have to think about how to write write my linear program. I just really need to write my, here's my state space, here's my action space, do your thing. It's I for me, because I've done enough work, that I feel like that would be the easiest thing. But eventually, the one that will do, that will what do you say, succeed, will be the one that does best. So maybe this is not the answer. I don't know, but definitely where I feel is the most flexible way to check off many of the objectives that we have in mind.
Yeah, thank you so much.
No
Really
worries.
enjoyed the talk again.
Yeah.
Thank you.
Oof. Okay, Igor's got a question.
Yeah.
Hi, Ari. How are you? Always love to hear your talks. I have a question.
Always love to see your face. How about-
Yeah, I'm here in person. So I have a question about how you plan to use contextual information, such as the presence of a quite obvious host galaxy, because it's not an easy problem, especially in case of kilonova, right? Because even as a scanner, as a robot, I would unfairly weight as something more relevant for follow-up a transient that has a big bright galaxy just next to it. But we know that for binary neutron star mergers, the separation between the merger and the host could actually be of more than 100 kiloparsec. So this is far from trivial a problem in my mind. How are you planning to tackle that, like now and perhaps in the future with LSST, with all the photoz's and so on?
Right. I don't have a current plan to tackle it. I think it's, as you said, it's quite challenging. Thomas had mentioned probably including offsets from sgrb hosts as training data, to probably then have, so first train on it and make sure that that can be extracted from catalogs and use it to inform the agent as in decision making. So offset from a galaxy with colors consistent with sgrb hosts would be a thing that Thomas suggested would be to try. Apart from that, I have no good ways of using host information at the moment. But if you do, can you tell me and help me? So it's a project that's there with a student waiting for waiting for a student to get that done, but definitely can be improved more. And people have complained about this. I don't have an answer.
So that's a challenge to those listening. Think about what to do about hosts. Okay. Any other questions for Ari? Okay, if not, huge thank you again. That was really wonderful, as always. So for our participants, we're going to take our break till 10:30, so half past, and then Brian's going to talk about scope stuff. And yeah, see you all in 30 minutes. Thanks, Ari.